Yes. Man, my wife got me tickets to some Fiesta event that we're supposed to go to tonight. But it starts at 10. What time's the game?
You can get the game on your phone now.
7? Well, hopefully I won't need to watch it. Hopefully by halftime it won't matter anymore. But all right. Everyone has their test? The grades were pretty good from what I can recall. I wasn't, but I graded them rather quick. So if you look through them and you feel like, wow, he took off a lot of points, but I feel like I had a lot here and you want to talk about that, then we can. I'll just say that today, immediately after class, I'm doing 2 observations today of adjunct faculty, so I will not be available after class today. But my office hours will be normal for the rest of the week. So if you just want to come by and talk about your grade, you can, just not now. Got it? How did you all feel about the test? Did you feel it was fair within?
It was fair.
I feel like I did a lot worse.
On this one than the previous one? Oh. Oh, you felt like you did worse than you did?
Yeah.
Well, let me regrade that. I'm just kidding. Maybe I didn't look at them hard enough.
Are we still going over 6.8?
Yes, we kind of just talked about it a little bit, right?
Very briefly.
It was over the half-life?
Yep. Hey. Right here, hold up. Where did I just? I know I just had it. Oh, there it is. I knew you were coming, so there you go. Yeah, so we talked about half-life, and I wanted to make a slight change to the formula we had, because I told you about this thing. Yeah, and I told you in class, and this is a mistake for me to have said it the way I said it, that T must be measured in, you remember what I said?
Years.
Okay, damn it, I was hoping you forgot. Yeah, the T can be in any increment of time. I have no idea why I said that. Here's what I was thinking. For formulas that involve finance, like interest rates, things like that, they always use T as years. And that I must have had a short circuit or something. T can be in any increment of time. It can be in seconds, minutes, hours, years, millennia, whatever you want. Okay, doesn't matter. As long as it's that same increment the whole way through the problem. Understand?
So when we did that review,
that review problem where it had seconds, was it seconds?
I don't know, but it's
that was hours.
Hours, then you could have left it in hours and your answer would have been in hours and that would have been okay. All right? I apologize about that, but
Hey, you're huge.
just clear, yes. Just to be clear, that's it. All right, so this formula works. This formula works for all forms of exponential growth and decay. What was it again that told us if it was growth or decay?
okay.
The K in the formula, right? If K was positive, it was growth. If it was negative, it was decay. So the next thing I want to talk about is Newton's law of cooling. I really like this topic. Most of the time, students like it too. Any of you ever heard of this? Newton's law of cooling?
Heard of Newton, but
Okay.
The Fig Newtons?
Yes, Fig Newtons. Isaac Newton.
Oh, I thought we were talking about the Fig Newtons.
Isaac Newton is a famous physicist, mathematician. He's the father of calculus. He invented everything, actually.
He also has some laws.
Yeah. Pretty impressive resume.
He also invented the Fig Newtons.
All right, so here's what Newton's law of cooling is. This is the formula for it. So I just will point out it is an exponential function, all right? The function u of t equals capital T plus U naught, or U sub 0, minus capital T again, so capital T is appearing twice here, and then e to the kt, where k is less than 0. So let me go through, just like we did before. I'll explain what all these letters mean, and then we'll see where this is used. All right? So first of all, let's get capital, well, maybe I should tell you what it is first, and then it'll make sense why we need all these variables. This is the formula that's used, not exclusively, but for finding, like if they find like a dead body somewhere, you know, like to figure out how long it's been there, right? Like a time of death. Now, it works if the body's found within a certain amount of time. Like, of course, if you come across a body that was, you know, been there for like 13 years, this doesn't work. But it works for the first, you know, day, right? Day or so. And so the formula is this: you have the temperature. You know, imagine you walk in and you find a. Okay, you're a detective. Okay, all right. You're not just walking around finding bodies, but. All right, so you're a detective, you walk in there, you find a body, right? And what they do is they take the temperature of the body at that point in time. They take a temperature of the what we call the ambient temperature, which is temperature of the surroundings. So that would be like the room temperature. And then from that, they can plug in and they can figure out how long the person's been dead, assuming that the person's temperature when they died was the average temperature, which is like 98.8, 98.6, whatever. I mean, we have acceptable average temperatures, all right? So if we assume that everyone is around 98.8, 98.6 degrees, when they die, your body starts to cool, right? Well, if you're in a room that's colder than 98.6, which most likely you are, then you will cool down. And if you're in this room long enough, excuse me, there's a temperature right here. It says it's 74.1. It doesn't feel like 74.1 in here, does it? No. But let's say it is 74.1 in here. If the body sat in here long enough, it would eventually reach 74.1. So the way it would look is something like this. If this is time, right, then at the time 0, which is when they died, their temperature would be 98.8-ish. Well, do y'all want to go with 98.8?
Yeah.
I don't care. 98.8 is fine with me. The temperature of the room, let's say 74.1, and their body temperature is not going to drop below that, right? If the room's going to stay at 74.1. But it will start dropping. And it will asymptotically approach that. And we can model that with an exponential function, but it's exponential decay, right?
Why is it exponential?
That's a little more involved. You have to be able to solve what are called differential equations, and from that differential equation you can come up with this. Differential equations are equations that involve rates of changes of things.
So I should have this conversation with you next year this time.
Yeah, when you take a differential equation class, you can see how you can come up with something like this. See, because as the body is cooling, its temperature is actually a function of how fast it's decreasing. So your current temperature somehow is connected to how fast your temperature is changing. That's called a differential equation. Think of it as like a more general example is like a population of foxes on an island. Think about if you had an island and you had rabbits and foxes, right?
Okay.
So what would happen?
Well, the rabbits will multiply.
The rabbits would multiply, the foxes would eat them, right? Fox population grows, but it starts to overwhelm the rabbit population. Rabbit population starts to shrink. Foxes don't have any more food. They start to die. Their population starts to shrink. Rabbits start to come back, right? You have this constant dynamic changing of populations, and they're connected to each other. To solve problems like that involves differential equations. This formula is derived from something like that. You have the body cooling, right? Its current temperature is based on how fast it's changing. So it turns out to be exponentially modeled. That's my short answer. Okay. Do you believe in the picture at least? Is that good enough? All right, so capital T is the, we'll say, can I say room temperature, even though it could be like outside? Yes?
Be just whatever temperature.
Surrounding temperature. Ambient temperature is the more technical word for it, ambient temperature. U sub 0 is the body temp initially.
Does it have to be a body?
Well, that's why I kind of stopped there for a second, because the book says object.
Okay, so object.
But are we sticking with the dead body in a room? Okay, because if I say, hey, we found a rock out there, people aren't as interested. Dead bodies, people like talking about dead things. So room temperature, ambient temperature, wherever you are. Body temperature, the temperature of the object when you find it. All right? And what else is in here? T, little t, time. And this is not specific. So time can be measured in any interval, just like before. Well, kind of like before. And K is going to be our constant. All right? This is our decay constant. Did I turn off?
Why do they have a K for constant? It's like somebody knew how to spell.
Oh, instead of C? Yeah, I know what you're saying.
I see what you mean.
We use C for a lot of reasons, and so I don't know. Some authors like to use K, some like C. Yeah, it's more of a personal thing than an accepted standard. Oops, sorry. Let me silence that. Okay, someone needs to relax.
Yeah, I was like,
You thought what?
yeah, I was like,
That is.
I was like, who's here? We should share.
All right, is there anything I'm missing here? I have capital T, U sub 0, T, K. E is always E, right? How about U of T?
Yeah.
What is U of T? What does the left side of this equation represent? It's the temperature of the body at time T. So the left side tells you exactly what the temperature is at a particular point in time. All right? This is Newton's law of cooling. Basically says if you have an object that's generating its own heat, or if it's generating, however, either it's cooling itself or heating itself, if you take that, you set it into some location with a different temperature around it, then it will begin to attain the same temperature around it. All right? It'll either heat or cool. Now, most of the time, it's cooling down.
It's kind of cool because if you think about it, like that's how they know, okay, well, if you're putting this amount of freezing water, this is how long you have to live.
Yes. It would probably be a different formula, because this formula is more based upon being in air. Because when you're placed into water, the heat transfers much faster. So you would have a different formula. Your constant would probably be much bigger. Your decay would be much faster. So, but yes, it would all fall into the same realm of this formula. All right, you ready? Let's try a simple example, then we do a hard one. Okay? Let's just try working with the formula first. All right, I'll do the example out of here, but I'm going to change some of the numbers. Okay, an object, this is an example. An object is heated to 120 degrees, and, well, what do you want? I was gonna go with Fahrenheit. Fahrenheit. Okay, so I'll just leave it like that. Yeah.
We use the American stuff.
Science major.
Well, I'll say Fahrenheit, but I won't write it. Is that okay? And placed into a room which is let's say 75 degrees. Okay, so that's what we're going to start with. You've got this 120 degree object. It's heated up. Put it in this room, and let's answer some questions.
What question are you asking?
Okay, here it is. If 2 hours later, the object is, let's go with 82 degrees. Then what is K? Can we find the growth constant? Or growth or decay? Yeah, decay.
Okay.
I always say growth because it's kind of like when you say, have you ever, you know what acceleration is? Okay, so when you accelerate, that could mean speeding up, changing your speed, or it could mean slowing down. They usually call it acceleration and deceleration, but if you say acceleration, it doesn't mean positive. It could mean negative acceleration. So same thing, when I say growth, you could have negative growth and positive growth. It's growing negatively. So okay, let's not get into it. All right, so what do we have here? Let's look at the things that were given. See if we can kind of come up with parts of the formula.
What, 82?
Surrounding temp would be 75.
Okay, so capital T is 75. I'm going to take the degrees off it, all right? Just going to put 75. Anything else?
U sub 0 is 120.
U sub 0 is 120.
No, we have the time.
Okay, yes. U of what? U of T. You know that at a specific point in time, it's 82, right?
Right.
But what point in time? 2? So you said
U
U.
up to-
Good. So U of 2 is 82, right? That's what we know from this information. We know capital T, we know little u, U naught, and we know that at a specific point in time, the temperature is 82. The object is 82. All right, so let's write down the general formula first, start filling in the blanks. I'm going to start with the most general, which is this. T minus U naught minus capital T e to the k little t.
Wait, I thought it was T.
Plus, I don't know why I did that.
That's all like, oh,
What you got there, man? Looks good. It looks good. You didn't bring it up for everyone, though. All right, so I can replace my capital T with 75, right? 75 is capital T. And then, is it?
Yeah.
No, it's just.
Oh, you said U of 2. Sorry, U naught is 120, right? These aren't changing, right? The ambient temperature, the room temperature is not going to change. The temperature the thing started at is not going to change. 120 minus 75 e to the, I'm not yet. I'm not going to look at a specific point. This right here is just a snapshot, right? Just at a specific moment, this is happening, right? But this is what I've got so far. 75 plus, what's that? 45 e to the kt. All right, so that's what I've got so far. What I really need to have a true function of t is I need to know what k is, right? So the question was, what is k? And we have not used this piece of information yet. I should be able to use this one piece of information to figure out what k is. So now from this, I know that if I plug in 2, right, I should get 82. So this side should be 82 when I plug in 2 for what variable? What is the variable here? This is little t, right? So I'm going to rewrite this now. This is a separate thought, though. Using the fact that u of 2 equals 82, I should get that 82 equals 75 plus 45 e to the 2k. Understand? This 2 is the t, 2k. The left side is the temperature at that point in time, which is 82. What type of equation is this? Exponential. Right? You're trying to solve for k. How do you get k out of there? How are you going to get k out of the exponent?
Natural log.
Natural log. Now or later? Do I need to do something, or can I do natural log right now on both sides?
You've got to get rid of the 75.
Bring the 75 over. Okay, yeah, let me do that. So subtract 75 on both sides. What do you get? 7 equals 45 e to the 2k. Okay, natural log now. Natural log now. Yes, no, maybe so.
Oh, wait.
Not yet.
Divide by 5.
Got to get the 45 out of there.
Divided by 45.
Divide both sides by 45. I'm going to need my calculator at some point here. Now can I do natural log? Both sides? Yeah, you should be able to do natural log on both sides now.
I guess you can.
And when I do the natural log on the right side, what do I get?
It goes away.
And you just get
Okay.
2k. All right.
And you can divide all that.
Man, I haven't used this calculator in a while. 7 over 45. So negative 1.8607. I'll just go 4 decimal places equals 2k. And divide that by 2. I get negative 0.93037. Or 8. I'm only going 4 decimal places. What did I say? The more you go, the more accurate your answer is. So what this allows me to do now is come up with a formula which will tell me the temperature of this object at any point in time, because now I know what the constant is. That's right. For part 1, that's all I wanted. So now let's go back. I just want you to rewrite the entire thing. So we had 75 plus 45 e to the negative 0.9303k. Not k, sorry, t. This is it. For this particular object, in this particular room, under the particular circumstances that it's in, what I mean by that is like humidity, things like that, could have a bearing on things. This is the growth rate or decay rate of the temperature. Now let's just check something real quick. I want to see if this formula actually works. What's the temperature of this object at time 0?
120.
Should be 120. Plug 0 in for t. 0 times this would be 0, right? E to the 0 is 1. E to the 0 is 1.
So
45 times 1, is 45 plus 75 is 120.
120.
Okay. Okay. At T is 2. We can't do it easily, but if you plug 2 in here, multiply, do e to that power times 45 plus 75, you should get,
You should also get.
if I plug in 2 here, I should get 82, right? Okay, you ready for the next question? Still pertaining to this problem. Part 2. When will it be, or when will it reach 77 degrees?
That's a very specific number.
What's that?
We gotta plug it.
Hour and a half?
We gotta plug it in.
So what is it that we want to know? When, right? When is T, right? We want to know at what point in time will the temperature be of the object be 77. In this formula, the left side is the temperature of the object at some point in time. We want to know when this is going to be 77, right? See, this is like our master formula now. We can figure out anything about this object. So if I take that, I replace the left side with 77 and go through, I can solve everything that remains for what? For T. How do we solve that? Subtract the 75, then divide by 45. You should get natural log 2 over 45 on the left. Do y'all know what I did there?
Yeah.
Subtract, get 2, bring the 45, divide it through, take natural log. What's on the right side? Negative 0.9303 T. And then get on your calculator, work that out. It's actually a bad girl. You see that? No. Never mind.
Oh, we missed that one. Is that a math joke?
No, it's not a math joke. Just trying to figure out how you can tell it's a bad boy, not a bad girl.
Oh.
You can tell, but you see? No, you can't see. Don't worry about it.
I was like, wait, is there some sort of math joke right here that we're missing?
Anybody want to tell me what they're getting?
I've got 3.346.
I'm getting the same thing. 3.346 is approximately T. So when will it reach 77 degrees? About 3 1/3 hours. From when, though?
From the initial time?
From the initial time, from when it was first placed in. Right? Because T is measured from, T is a measurement of time from when you start the clock, which is when the object was placed in the room. So it took 2 hours to reach 82 degrees. It's going to take 3 1/3 hours to reach 77 degrees.
3 hours, 20 minutes, and 45 point something seconds.
Good.
I'm glad somebody took the time to do that.
I have one last question. When will it reach room temperature? No, the room temperature, not. What was the room temperature?
75.
75. So you're just going to set the same thing up, right?
Yeah.
Let's see what happens. Uh-oh. You've got problems. But we're doing math right now, so we won't talk about those, okay? Your problems extend far beyond this problem on the board. What is the problem here? We run into a problem.
It's going to be 0.
We get 0 on the left side, right?
And
And
when you
the-
divide 45, it's still going to be 0. So you end up with
Zero.
0.9.
And you can't have log of 0.
That's right. You can't take the log now. Right? Do y'all follow this? So what's going on here?
It'll never reach room temperature.
It will never reach room temperature, but that kind of seems ridiculous. That if it sits there long enough, it's going to reach room temperature, right?
Yeah.
That's why we call these mathematical models, because we're modeling the decay of the temperature. You know, we found the body or found the rock, whatever is 120 degrees here. The temperature of the room is 75, and we know that it does drop, but it's an asymptote. So it'll get pretty darn close, but never there.
Determine what that asymptote is.
The asymptote's 75.
I mean, when is it?
It never,
Bless you.
I know. Let me rephrase the question. My question is, how do you know when it gets close to the asymptote? When the asymptote?
My only question would be, how close do you want me to be?
I don't know. Then half 20.
Yeah, so I mean, it's a matter of closeness then. And that's why this is a good model. It's good enough for, I mean, because look, honestly, I see your hand, hold on just a second. At some point, if I take the temperature of a body in a room and I take the ambient temperature, we can start getting real picky because the temperature right here is different than the temperature right here, you know? The air in this room is not uniformly distributed temperature. So if you want to start getting real picky about, well, when does it reach exactly 75, I don't even think the room can be considered to be exactly 75. So it's good enough. If that makes sense.
So that's your answer.
No, my answer is that I can't answer this. Okay?
mathematically, it will never reach.
It won't with my model, all right? With my mathematical model, it won't ever reach room temperature. No solution. Yes, ma'am.
No, I think you kind of answered my question.
Sure? Okay. All right. Look, what we do in the real world is we take problems and then we try and find mathematical ways to solve them. And the mathematics we use are called models. They don't have to be perfect. They have to work within a certain precision that's acceptable. And as long as you're within that accepted precision, then you're okay, right? It's, let me give you an example. Has anyone ever put a spare tire on their car?
It sucks.
No? Okay. So if you've ever been on the side of the road and you have to put your lug nuts on and you tighten them up. Now the manufacturer says there's a very specific torque for those bolts. You just tighten them up and get yourself to wherever you need to go, right? And then you go to like whatever, the tire shop, and then they go and torque them? Hell no, they just get their impact wrenches and and they just, that's supposed to be an impact wrench. That wasn't very good.
There you go.
No, I won't even go for it. Okay, so you know what I'm saying. With lug nuts on tires, I mean, we got to just be close, right? Now, lug nuts on an aircraft tire.
Now that's different.
Now, you've got to have that right. Why? Wheel comes off, you lose all 200 passengers on the plane when you're trying to land, right? So there are very specific tolerances that have to be met, higher standards. And that's the way it is with mathematical models. We make models to represent situations that we deal with in the real world. Some models are good enough, and sometimes we have to make them a little better, and a little better, and a little better. And that's why physics gets so difficult, is because we can have very simple models for very simple situations, but as you start to throw more elements into it, the models get more complicated. So we're okay with the fact that this doesn't truly ever reach room temperature. We're okay with that because it's close enough. The model works good enough. All right, I'm going to move on because I have now the hard question. We're going to move away from that example. We're going to start with a new one. Ready? Detectives. We're the detectives, right? We'll call this we'll even title this is going to be the dead body problem.
Dead body 1.
So we find a dead body.
Whose body is it?
A former student who was trying to get too much extra credit cut all their fingers off and bled out.
Awesome.
Sweet.
So it's your fault.
It's my fault. We find a dead
We
body,
have to bury this thing.
and
Doesn't matter how long it's been there.
oh,
We're burying the body.
the temp
If you don't get caught,
is
you get an A.
You get an A+ for just killing yourself.
83 degrees.
That's for the semester too.
That's
not just
terrible.
credit.
That's terrible.
You get 30 extra points to whatever your grade is.
No, what's the temperature in here?
Okay, okay, so we find the dead body, the temperature is 83 degrees of the body, all right? Room temp is
You should just give us the temperature in the room actually.
70, let's make it a colder room, 72 degrees. How long has this person been dead? Now, I want you to think about this. I'm going to step out for a few minutes to let you think about this. It is not as clean and easy as you may think. So you can talk to each other. I would like to come back in here in a few minutes and have
Actual.
either you telling me, yeah, this is hard, or like, no, I think this is the way we'll do it.
We got
Yeah.
this.
We got it.
Okay? It will not follow exactly the way the last one just did, though. It will not be the same thing.
We can at least write
You have a lot less information here, don't you?
Yes.
Right? In the previous problem, we had this, right? We had the initial and we had the room. But then I gave you something else, right? I told you 2 hours later it was this.
U of 0.
Hmm?
No, you,
there. The time is up there.
yeah, what's your temperature now?
So look, please understand that what I want you to do is think about this from the point of view of a detective. All right? What would you do now? Okay?
Degrees.
We're assuming, yeah, we will assume in this, assume 98.6. Okay? That's the temperature when the person died. All right, is that good? Let me see what you do with that. Okay, so any ideas?
Well, I think I might
What do you
figure
got?
something out.
I don't think I did it right, but I did, I sub U of T for U of two, kind of to like make a made-up time.
Mm-hmm.
And then so I had 197.2 equals 72 plus 98.6 minus 72 to the K of two. And then I solved it for K.
You don't know if that's the actual constant.
I know, I made it up to find K
Okay,
as kind of.
I think you're on the right track in terms of your idea. But remember, I'm asking you to think of this as a detective. Do you have enough information
No.
to solve the problem right now?
No.
You don't. Right? So I didn't want you necessarily trying to solve it algebraically. I wanted you to try and solve it in terms of what do you do now?
Oh. Well, we go get a.
I mean, here you are, you're standing there, it's a dead body, you took its temperature.
Oh, and then we can take another temperature at a later time.
Okay, that's the way you would do this. I knew you would be upset, but I want you to understand how it's done, right?
That way, in case you become a detective instead of a doctor.
Well, no, because they just have an app, they just plug it in. But
They can also do it by
how long
flies,
has this
and
body
we
been
can get the
dead?
magnets and see how.
oh, because our body has flies on it too.
And then we
Okay.
can see rigor mortis,
Yeah.
if the body's
Yes.
tense, then,
Yes, no, there are a lot of different things depending on how. I mean, there's entire colleges that have departments that have dead bodies out in the field, and they look at different scienarios and stuff.
Like
And
when, Atlantic State.
it's pretty cool. Anyway, okay, that's science for you. All right, so look, realistically, what we would have to do. Well, let's see why this isn't enough information. Can we do that first? Why we cannot do it with what we have? What we know is that this person, when we found them, they've been dead for a while, haven't they?
Obviously.
That point in time, right, we don't know what it is, right? So, look, we found them. Let's call T sub F the time when we found the body, okay? That's when we found it. Isn't that also the time, how long they've been dead?
Yeah.
Right? When we found them, that's how long they've been dead. What we know is this. U of T sub F is what? 83 degrees. Y'all still with me? All right. What else do we know? Capital T is 72 degrees. And do we know the body's temperature initially?
98.6.
Did we use 6?
Yeah.
I think I said 6. Sorry, we're going to go with that.
That's what it says here.
All right, so this is very similar to what we had in the previous problem, right? With one exception. We knew that was 2 in the previous problem, right? We knew 2 hours later we had this, right? So if I try and set this up right now, using just these two pieces of information, I know that U of T is equal to capital T plus U naught minus capital T e to the kt. The way you say that, U naught. U naught. Like not like you tie a knot, but I heard some people will say U sub 0, but that's most of the time that's the way you'll hear people say it. U naught. Not meaning 0, nothing. All right. Let's replace the things we definitely know. U of T equals the temperature in the room, 72, plus temperature initially, 98.6, minus 72, e to the kt. And this means U of T equals 72 plus, what's that?
26.6?
26.6 e to the kt. So that's the formula so far, but we still don't know what k is. Now, are you following that since we don't know this, Like we can't plug in like we did before 2 here and it spits out a number. So there's no way we can solve for k if we don't know t, right? So we sit there and we go, okay, well, we need more information. So what we do now is we wait, all right? We've got the body there. We wait for police are, taping off the scene, and we wait for about an hour, let's say, and then we take the temperature of the body again, all right? So we take the temperature of the body again, and let's say 1 hour later, the body is, got to make this up here, 79 degrees. It was 83, right? No? Yes. You with me? How can I write that in the same fashion that I wrote this? U of?
Sub-zero.
So U of T sub F plus 1, right?
Yeah.
So it's whatever the time I found it plus 1 hour is equal to 79 degrees. Yeah? All right. Things are about to get pretty crazy. Are y'all ready? I have 2 pieces of information now, but with both of these, I still don't know what this T sub F is, right? That's the goal, to find T sub F. And this is the formula right here that I have up to this point. Bless you. Is everyone on board? Okay, here we go. I'm going to rewrite this formula using this piece of information right here. So that means that 83 is the left side, equals 72 plus 26.6 e to the k times what? T sub f, right? No, just T sub f, because I'm doing this one. Okay? Everyone agree with that? Okay. The other piece of information we have this, and we have this piece of information, which says that 79 must be equal to 72 plus 26.6 e to the k times what? T sub f plus 1, like that. Understand what I've done there? It has to be in parentheses, because k gets distributed to each one of those. Y'all still with me? So I have
Why is it not sub, like that?
This?
Oh, okay, yeah, okay. Why is it not outside the parentheses?
why is what not? What?
Well, in the other one, you wrote it T sub F plus 1, all of that subscript. Now it's not? Or no?
Where did I write?
Okay, maybe I just wrote it in.
Oh, this plus 1 is not subscripted.
Okay.
This is actually right, like that's the time we found the body. This is 1 hour later.
Okay.
Now this leads us very, very nicely into what we're supposed to do for the next part of the class today, which is to think about what we have here in terms of equations. We have one equation, right? How many things do we not know in this equation? 2. I don't know what k is. I don't know what T sub f is. I have a second equation, and there are 2 things I don't know, k and T sub f, right?
But you do know what it is 1 hour later.
Yes. But in general, I have 2 equations, and I have 2 things I don't know, right? If you have one equation and 2 things you don't know, you'll never get an answer. Let me give you an example. If I give you x plus y equals 2, there is not a unique answer to this. There's an infinite number of answers, right? 2 and 0, 1 and 1, 3 and negative 1, right? One equation, 2 unknowns, there's not a unique answer. But if I give you 2 equations with 2 unknowns, there is one answer. And that's, again, where we're headed with chapter 12 after this. But my point of me telling you this is that we will be able to figure out what K and what T is as long as T sub F, as long as we have two equations. So here's what I'll do first. I'm going to distribute this K through to both of those. Is that all right? And I'm not going to rewrite the whole thing. I'm just going to do it and write it next to this. It'll be K times T sub F plus K times 1, which is K. Do you follow me? That's what would happen. Now I'm going to use properties of exponents. Remember this property that says if I have x to the n plus m, that actually comes from doing x to the n times x to the m. So if you have the same base, two exponents, you multiply these, it's the same as one base adding the exponents, right? I'm going to go this direction. Do you see I have a base raised to two things being added? I'm going to rewrite that as the same base twice, each of the exponents separated in multiplication. So this becomes 7 equals 26.6. I went ahead and did the 72 to the other side. Okay? E to the K times T sub F times E to the K. You all right with that? Sure? No questions?
And then I just divide the 26.6.
Why again
Not
would the plus 1 turn into a plus K?
Remember, it was K times T sub F plus 1. I distribute K to here, I get K times T sub F. K to here, I get plus K. Distribution. Do you see what I circled in red up there? Right there? Or not up there, right there? See that? Do you see that right here? Are those the same? Yes? Move that 72 to the other side on the first equation. What would you get? 11, right? Equals 26.6 e to the k times t sub f. Yeah? So this right here is this, isn't it? And what is this equal to? 11. So I'm going to rewrite this now. 7 equals 11 e to the k, and I only have one variable now. 7 equals 11 e to the k. And what? Okay. It's like a substitution. I'm saying from the first equation, I know that if I could solve for this, right? And get that? And that must be 11. But I can't figure out what these two are because I only have one equation. When I work with this second equation and split it up this clever way, this first piece right here matches this. And so I can replace that with 11. Pardon?
So if the two first pieces matches, then what do we do with the second piece of that?
Where?
The e to the k.
It's right here.
Yeah, but what do we do with it?
Well, this equation becomes this equation.
Now you divide by 11.
Now I divide by 11,
Then do natural.
and then log on both sides, and I'll be able to get what k is. Look at these as two separate ideas. This idea like this turns into this. Okay, great. And then you go, oh, shit, look, this is that. That's 11. And you replace it.
So once you get K, do you plug K back into the first?
Okay, one thing at a time. Let's get k. So 7 over 11 equals e to the k. And now log on both sides. Natural log of 7 over 11 equals k. And so k is approximately what?
Negative 0.452.
0.452? Something like that? Anyone else get that? Yes? All right, we know what k is. Yes? But that's not what we wanted, right? We want to know T sub F. That's the temperature of the body when we found it. So look, if we go back up to this right here, right? Go to this equation right here. Let's write it down. 11 equals 26.6 e to the, but we know what k is now, don't we?
Yeah,
Negative 0.452 T sub F. The temperature when we found the body. Can you solve this for T sub F?
Yeah,
How?
by just doing what you did.
Okay, so I will
The natural log of-
divide by 26.6. Take the natural log on both sides.